RaptorX. This is the topic I'm talking about. My name is James. I'm a software engineer in Facebook working on Presto. And the topic here is to how we achieve making Presto 10x faster on a Facebook scale petabytes or exabyte of workload. So to bring up the context is like disaggregated storage is an industry trend, right? We have like Snowflake, AWS, or BigQuery, or Google GSP, all of the things they have disaggregated storage, right? So you have your data stored on a remote storage tier, and you will have your compute on another tier. And those two things are disaggregated. The benefit of doing that is your workload might be skewed on either compute or storage. It helps you to leverage or helps you to scale independently of your storage versus compute. So if your workload is CPU bound, you just add machines to increase compute. If your workload is storage bound, you just add machines to scale your storage. These two things nicely kind of separate the compute and the storage in a way it is more cost saving and more efficient. So this is a trend in industry to move forward. Okay, well, we know like disaggregated storage is a good thing, but it also brings new problems to the Presto ecosystem. Okay, or any other kind of disaggregated compute and storage system. That is the bottleneck over the wire. You're gonna transfer your data and the metadata over the wire between your compute tier and your storage tier. In Presto specifically, the graph here shows like you need to have RPC calls to your Hive meta store to get partitions. You go to your remote storage to list the files. Then you need to schedule your files, right? You have a lot of RPC calls to open your file, to retrieve your file, and to read data from the warm storage, from the remote storage. So in this way, in most cases, network and I/O will be your bottleneck to prevent you achieve faster latency. Okay, and that is reasons like within Facebook, we started this project codename RaptorX, aiming to boost the performance of Presto with remote storage or disaggregated compute kind of architecture by 10x faster. And RaptorX, the very much representative feature out of it is the hierarchical caching. So we built hierarchical cache within Presto, or specifically the Presto Hive connector, in order to achieve way faster latency compared with just pure Hive connector. So the idea is actually very simple, right? We know that the disaggregated or remote storage is going to be I/O bound over the network. Why don't we just add cache to each layer, including the metadata path, the data path, and a bunch of compute actually, to provide way faster access if we can cache them locally. So that's the main idea. So we cannot just blindly cache the data or metadata. And in this talk, I'm going to give a very brief idea is like how we cache them intelligently so that you can maximize your cache hit rate and boost your query performance. Continue. In the remainder of this talk, I will go through all the caches we built for each layer. And we were starting from the simplest to the hardest. And to provide the audience a idea is like, hey, what are the caches we built and what are other intelligence we here refers to? Okay, so before we go into that, that's coming back to the picture of to understand the normal workflow of how Presto Hive connector works. So during the planning phase, we need to ask the meta store for the metadata, right? And the scheduler will ask the remote storage for a list of files. And then a scheduler can do the scheduling. On the worker side, we first receive the files from the scheduler and ask remote storage to open the file, read the file footers, no matter it's a work format or Parquet format, we need to read a footer. Then based on the footer, we retrieve, okay, what are the data blocks or data chunks we need to read. Okay, once we read them, we will do the compute on the leaf node, whether it's drawing or aggregation. We'll do compute and do the shuffle coming back. Okay, so we all know that these are IOs. We'll start with the simplest one, that is the metadata cache. This is the cache we introduced in order to reduce the Hive metadata RPC call overhead. The idea is really simple. It's like, why can't we just cache the metadata on our coordinator? Why we need to ask for the table information, partition information, every time I receive a query and I go to Hive metastore with a bunch of round trips? The major challenge here is like all the metadata is actually mutable. We cannot just cache them on coordinator blindly because people can change the metadata all over time. We need to have a concept of versioning. That is called a version of metastore cache. So upon receiving a query, the first thing we do is actually to check, hey, do I have this cache for this metadata? Do I have a cache for the partition or the table, right? If I have it, I will get the version of that partition and ask Metastore, hey, is this version up to date? If this up to date, we will just use the cached version of the partition information to proceed with our workflow. If it's not to update or it's not even present in the coordinator cache, we'll go to the Metastore, say, hey, give me the latest version of your partition together with your version number, right? Then we cache them. So we still need to bring the RPC between the coordinator and the Metastore, but the RPC is much more lightweighted because instead of getting an entire partition information, we are only comparing the version numbers between those two. So that in our workload in prod traffic, it shows 20% of latency decrease. Okay. Now it's the next one is the file list cache. This feature is actually contributed from open source. It's from Uber and Pinterest, if I remember correctly. So this cache is also really simple. So when we have the partition information, right, the scheduler needs to ask remote storage what are the files we need to read per partition. And we know that per partition in Hive word, the number of files or the file contents is immutable. We are not going to change the file content within a partition, right? So given a partition path, why can't we just cache all the files on a coordinator so that during the scheduling time, we don't have to ask for remote storage to list the files? Okay, usually the remote storage like Industry S3, like Google Colossus or Facebook Warm Storage, to list the files of a partition is non-trivial amount of time. Usually it scales from 10 milliseconds to 100 milliseconds in order to get the number get a file list in a partition. So with this cache, we can avoid overhead, especially if you have a lot of partitions or you have a lot of files in the partition, that can significantly reduce the metadata call to your remote storage. Okay. So these two are the simplest cache on our coordinator. Then we'll talk about more complicated caches, how we do on the workers. And that is actually where we get the majority of the gains. I'll achieve 10x faster Presto by using RaptorX. Okay. The first thing we want to keep in mind is like, if we want to cache something on the worker, no matter is data or metadata on the worker, we need to do something to our scheduling policy. That is because if you cache something on your worker, for example, a file or a footer or metadata of a file, you want to make sure like next time you read the file, you are using the same worker, right? Our current scheduling policy for Presto is by doing load balancing. Means like if you have a file to read, the scheduler will ask, hey, which worker is with the most free splits to run on, and assign that file to that worker. This kind of load balancing works if you want to kind of balance your hard shot or whatever. In a cache word, this doesn't work because that will disrupt the cache locality. In this way, what we bring is affinity scheduling. Means like we use the file path as a hash to always send the file to the same worker as much as possible all right, to leverage whatever is going to be cached on the worker. So that every time we read a file, we use the same worker, and the worker has a full context because it has a high probability of the cache. Of course, in this way, we are still facing like node is gone, node is done. We are adding new capacity, removing capacity. And there are workers that could be very hot. So in this way, our scheduling policy should be soft. We highlighted the scheduling policy to be soft. Affinity Scheduling means that if we know the worker is not available or the worker is too hot, we are still going to fall back to a load balancing way so that we don't overwhelm the worker by not using a cache. Okay, so we have the scheduling policy in place. With that, we can build the cache on the worker. So the first thing we want to build is actually the footer cache and the file descriptor cache. When a worker reads a file, the first thing it needs to do is open the file. Okay, for any remote storage at 3 clauses, warm storage in different industry companies, this call is very expensive. Usually take tens of milliseconds or even longer to open a file. Once we open the file, the reader needs to understand where we need to read within this file. So the first thing it needs to do is to read the footers. No matter it's a file footer or stripe footer, it needs to read so it knows, okay, which column it is within the file. So why don't we just kind of cache the file descriptor and the footers in memory or in the worker in a way that we know these things are the hottest spot within a file. No matter what columns you're gonna read with the file, footers and the file descriptors are the things you have to read, okay? And that is very hot. Suppose you have 20 footers in your file, you have to read all of them, no matter what. So in our implementation, we cache them on the workers, and we do see 40% of CPU and a latency reduction in prod, so that we don't have to go to remote storage to say, hey, give me the footer, deserialize it, and retrieve which column it resides within a file. We skip all the things, and we just directly read the cache, which is deserialized, and go to the file and read them from remote storage. Okay. Once the file footers and the file descriptor are cached, now it's the major feature we are facing here. That is the data cache. That is actually giving us a 10x performance boost in prod. So the data cache is essentially the actual bits we cache from remote storage. We don't deserialize it. We don't decompress or decrypt it. We just cache exactly the format of your remote storage bits on the local storage, which we use SSDs. Okay, and the cache library we use is Alluxio. We know Alluxio is a pretty well-known open source caching service. And in the past year, we worked very closely with Alluxio to build a library version of it and embed it with Presto code base. So it's very simple. With the library, just turn it on and everything just works. The only thing to specify is, hey, what is the SSD path I need to do my cache and how large is my cache overall? Usually in Facebook production environment, we use 1 terabyte or 2 terabyte per worker as the cache size. So how Alluxio works is pretty intelligent. In this way, when a Hive connector or Hive reader issues a read to the remote storage, usually the way we issue is by issuing a range, right? The range usually is from the footer. Footer tells you, hey, this column is from range, for example, 1.21 megabyte to 5.6 megabyte, okay? So the reader will issue this read to Alluxio. Say, hey, Alluxio, read this range for me from the remote storage. And Alluxio algorithm will say, okay, if you are reading from 1.1 to 5.6, I'm actually going to issue the range from 1 to 6 to strictly cover your range, but with 1 megabyte alignment. Okay, why we have this alignment is because of this. So once we have this aligned read from Alluxio to remote storage, Alluxio will receive it, all right? And it will chop the chunks into 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 6 megabyte. And store the small chunks, which are aligned megabytes of chunks on a local SSD. okay? And if later on, a Hive connector asks for another range, which could be 2 columns or other columns with different ranges, for example, 4.3 to 7.8 in this case. Then what Alluxio does is, okay, it needs to look at my local cache. What are the chunks I have already cached? It knows like, okay, 4.3 to 6 megabyte I already have based on my previous cache. Then I'm going to return this part of the data directly to the reader. And I'm going to read 6 megabyte all the way to 7.8 with alignment, which is going to be 8 megabyte, issue to the remote storage, and return to the reader, as well as cache this 2 chunked 6 to 7 megabyte and 7 to 8 megabyte on local SSDs. So the nice thing about this chunk is not only we have a coverage of your new read, so we know like what is the intersection of your new read, what is included, was not included. For the included thing, we just return directly from cache. For the excluded thing, we just read from remote storage and cache on local disk. And also, this small chunks provide us a nice way of evictions. Eviction is super important because we know that within a file, there are some spots that are very hot, there are some spots that are not hot. So the policy, eviction policy we use is LRU. If we know there are some 1 megabyte chunks that are frequently used, we will kind of pin them on SSDs, right? Based on LRU or LFFU eviction policy. If this 1 megabyte chunks are not so hot, we know like, hey, they're going to be not accessed so often, we will just evict them with this 1 megabyte as a whole. So this 1 megabyte alignment provides a nice unit for caching as well as eviction. Okay, so that is the data cache. And the last cache I'm going to talk about is the fragment result cache. That also brings us a lot of performance gains, not only on latency, but also on CPU decrease. Okay, and this is the last cache I'm going to talk about. It's the most complicated ones we built. The fragment result cache is with the idea is like we don't have to compute the same fragments that we have computed in a previous query. In order to illustrate the idea from to explain it easily, we provide 2 examples. The first example is like, suppose we have a query, very simple query. You just select the sum of a column from a table with a partition from March the 22nd to March the 24th. Okay, so once we run this first query, we know that the worker will compute the partitions for each of this date and do the partial aggregation and compute based on the leaf node, right? So once we run the first query, the worker is actually going to cache the computed result for the 3 partitions on the corresponding workers. So once we have run the first query, we will have 3 pieces of the partial computed result for the DS of March 22nd, 23rd, and the 24th, and cache them with the pre-computed result. Okay, so if next time a user say, oh, I want to actually not only see the past 3 days, I want to see the past 5 days of the aggregation of this table, the worker will know, oh, I know like the ranges you are querying over, 3 of them have already been computed in the previous query, right? And only 2 of them are not computed. So in this way, why can't we just leverage the pre-computed result and send back them to the aggregation node and do the compute for the 2 DSs that have not been computed? Okay, so in this way, the query plan will look something like this: is you get the cache result for the 3 partitions and do the compute for the remaining 2. And after this remaining 2, this 2 computed result will be cached as well. And all these 5 partitions will finally be streamed into the final aggregation node for the final aggregation. Note that all this partially cached result only applicable on the leaf node, so you can prevent your redundant compute for your scan, project, filter, and aggregation, which is partial. Okay, So intuitively, user or audience will ask the question, is this going to be effective or not? Because aggregation shapes or leaf query plans, they change a lot. They are very kind of flexible, right? How you can maximize your cache hit rate. In production, actually, we see this is very, very productive. This is very, very efficient. The reason is we are doing normalization and stats pruning based on that. For example, suppose we have a query, right? And this query is querying a DS between March the 22nd and March the 26th. And it also has a filter of time greater than now minus 3 days, which is to provide what is the data from now and 70 hours from now, 72 hours from now. Okay, so the query plan will look something like this, which you have your scan node and you have a filter, and the filter changes all the time across your queries, right? It changes all the time across your queries, and that is going to give you an impossibility of how you can make a cache hit, right? Because your query plan changes. You cannot reuse the same result of your previous query because they don't have the same plan. But in this way, what are we doing is, hey, what if we know that your condition can be removed from your query plan? For example, now minus 3 days is always going to be true for your partition March the 23rd. Actually, you can just remove this filter out of your plan and make the plan very, very generic by only doing in a table scan of your partition followed by a partial aggregation node. So in this way, we are relying on the stats of your partitions to help you to do the pruning. So if you know your stats for that partition is having a full overlap of some of your filters, we can confidently say we are going to remove that filter from your plan. And this is going to maximize your cache hit rate. Okay, and all the steps, we call it query shape or plan node normalization in order to have a very generic plan template so that the next query will have the same template and provide a cache hit rate. This thing is a little bit complicated. I may lose a lot of audience, but the high level overview is we do normalization in order to maximize the partial result cache hit rate. Okay, so that's all the caches I'm going to introduce, and here's the benchmark. We did a TPCH benchmark on 100 machines, each machine with local cache with SSDs. We do see some of the performance, for example, Q1 and Q6 for TPCH, they are like 5x faster than the ones without cache. And for other queries with joins and other heavy compute, we also see from like 2x to 10x kind of different performance on the TPCH benchmark. Okay, so the final things about RaptorX is it's not a toy, it's not a research project or idea. It has been fully battle tested within Facebook. It has been installed and deployed for more than 10,000 machines within Facebook and running for a long while. It's also a project that we are bringing in to consolidate a lot of different kind of ad hoc engines, which are co-located, like Tim mentioned Raptor connector, right? Raptor connector has been deprecated within Facebook because it's not scalable, it's not disaggregated storage. So we completely use this project to deprecate Raptor and some other kind of co-located storage, which are fast, and all of them becoming a RaptorX. It is the engine of choice for Facebook for interactive queries. And finally, what are the things to come beyond RaptorX Cache? RaptorX is a code name. That's the takeaway of this talk. It's a code name. It aims to boost Presto query performance, not by only using cache, but with many other investments that we're doing. So currently, we are working with C++ native eval to build the same thing within C++ eval for Presto. And we are also investing better affinity scheduling policies with consistent hashing and a bunch of other things to overcome this nodes coming up and down, all the things. We are integrating with a disaggregated coordinator so that the coordinator will know, hey, we will have the same scheduling policy as well. The two new features we're building to boost code performance are materialized views to leverage the pre-computed aggregates. Also, we are investing in the Z-order clustering so that we have better pruning for an arbitrary combination of features. So that's it, and that's the end of the talk. And thank you.